Hello students, let us begin lesson 13b, the optional part of lesson 13. Here, I'm going to require everybody has some sound knowledge in linear algebra, otherwise you can just skip. We are not going to use lesson 13b in lesson 14. Everything here will be used for lesson 15, which in turn is mainly an optional topic. Okay, alright, let's begin. Determinants. We already discussed the determinant of order 2, here, AD minus BC, and we used it for inverse matrix formula and also for Wronskian formula. Let's see, here we go, Wronskian determinant. And where did he use it? We used it to check whether a pair of functions y1 and y2 are linearly independent or not. And there was a nice theorem that the determinant, this Wronskian determinant, is either constantly zero or never zero. Another use, this was used for the denominator of the variation of parameter formula, which is, let me get the file. Yes, here we go. And let me see, is there a formula? Yes, there is. Yeah, here. Particular solution requires Wronskian in the denominator. And the Wronskian is this quantity. So yes, we had been using this. How about determinant of order 3? Now, here's one way to describe it. And the crisscross rule associated to determinants of order 3. So multiply all these diagonals in principal direction, positive direction, and the other diagonals in negative direction, and add them all up. You see, we have one diagonal, but the other diagonal will have to continue. And then from here, continue. So all these are positive direction, and the other direction we have all these negatives. So 3x3 case is far more complicated than 2x2 case, but still it follows a crisscross rule. Another way to write it is through a recursive definition. Concentrate upon the row here, and then A11 times something, and A12 times something, A13 times something, and A11 times, now remove the first row and first column where A11 belongs, and what's left is 2x2, and take that determinant. And then we do the same thing here, A12, and this belongs to the first row, and then second column, so remove those. So what's left is this matrix, and take that determinant. And we have the third number, A13, and this belongs to the first row and third column. So remove those, and what's left is this matrix, and take the determinant of that t/2 matrix, and we have this plus, minus, plus alternating sign, and adding them up, we get the determinant. And the second rule here, this can be extended over to arbitrary order because this is basically a recursive definition. If you have n by n matrix here, do exactly the same thing to the first row, then what do we have? We have something times now n minus 1 order, and something times another n minus 1 order, something times n minus 1 order, and that continues. So basically, from 1 by 1 we get 2 by 2, from 2 by 2 we get 3 by 3, and from 3 by 3 we get 4 by 4, and 4 by 4 we get 5 by 5, and so on. And if I already have n minus 1, then from the same recursive rule we get determinants of order n. And that can continue forever. So yes, we can define determinant of arbitrary order using this formula. And then there's I'll be more general form like this, but then again, this really belongs to linear algebra, not here. So let's just move on. Some basic properties of determinants. Oh, this 2 belongs to linear algebra, too complicated. Okay, here are some things to remember. Determinant of transpose stay the same. Determinant of product is product of the determinant, and this may be a bit useful for our purpose here. And then this one, determinant of inverse, it's 1 over determinant, and this one can be deduced from here. So from here, if I apply B as A inverse, so instead of B, if I put A inverse here, then determinant of A times A inverse, what is this? That's determinant of the identity matrix, isn't it? Because A times A inverse is identity, and that's just 1. Oh, by the way, how do we get determinant of identity matrix is 1? Maybe I have to go back there again. So, oops, sorry about that. Okay, here, replace one of them by I. Then this is equal to determinant of A. That's because A times I is just A. So we have this and that cancel each other out. We get determinant of I is equal to 1. This is what we get. And you can do exactly the same thing even if you multiply the other way around. In that case, again, we can divide those out, and you're going to get determinant of I is 1. And then use that here, then you're going to get that. That was a quick derivation, but if you don't follow all those derivations, that's still okay. You can still use this. Determinant of product is product of the determinant, and then determinant of inverse is inverse of the determinant, reciprocal of the determinant. Okay, those are basic properties of determinants. Now, some further properties of determinants. Oh my. There are all these, and I'm not going to prove any of those. Let me just give you the statements. So, all the column vectors are linearly dependent if and only if determinant of the matrix is non-zero. And we'll have the same thing for row version as well. Oh, wait a minute. Okay, this is just linearly dependent version. Okay, so that was really trivial. Let me rewrite it like this. How about all those? All the row vectors are linearly. Oops, what's happening? Sorry. Okay, sorry. System just shut down and I have to get back. And where was I? Okay, we just discussed this one. All the columns are linearly independent if and only if determinant is non-zero. And then I was writing down the row version. If all the rows are linearly independent, then again, if and only if the matrix is non-zero, the determinant of the square matrix is non-zero, you can say the row version as well. And then the linear independence of all those are related to the existence of the inverse map, because let's see, the linear independence of all those column vectors actually mean the dimension of the image is the same as the dimension of the original space. So consequently, kernel is zero-dimensional, so the linear map is 1-to-1. So it is invertible. If you didn't follow, that's okay. Determinant is non-zero if and only if matrix is invertible. And then now we establish the invertibility, we can apply this to system of linear equation. You see, we already discussed it before. Oh, never mind. Determinant is non-zero, then the system of linear equation in matrix form, Ax equals to b, has a unique solution. And let's see, do I have simple proof? Yeah, luckily I have simple proof here. We can simply multiply the inverse and we can find it. And the other direction is actually far more significant. That'll be hard to follow, but simple version, you can remember this one. The other direction, maybe we'll do it in different class, linear algebra class, Maths 3330. Now, why did we discuss all those linear equations and stuff? Because we needed this Cramer's rule. And you can use the theory of determinants and all to find out an explicit formula for the solutions of any system of linear equation, actually. So if you have any system of linear equation like this, and then you can get all those coefficients and form those into column vectors, like here, as I did all those color coding, and then set up the determinants and then replace the jth column with the right-hand side, this part. And then that's going to be the solution. So we have algorithmic solution as a matter of fact. So if you have algorithm to calculate the determinants, yes, we have those recursive algorithm, then you can find out the solutions. So computers can handle these kind of things, even though there's actually easier way to handle this, more computationally effective way to handle it, but this one works anyway. And applying those to systems of linear equations, you can actually get the inverse matrix formula. Some people call this one as Cramer's rule, but our linear algebra textbook calls this one as Cramer's rule, and this is Cramer's inverse matrix formula. And as a matter of fact, in lesson 15, or the latter half of chapter 9 of our textbook, we use some of these, but in our textbook, mainly for 2x2 case only. Well, let's see, we have some time left, so let's discuss the application of this Cramer's formula. How did it deduce the inverse matrix formula for 2x2 matrices? Well, better ways to calculate it by direct computation. It's easier that way. Multiply this inverse matrix formula, as you see on the right hand side, times AD minus BC, the original matrix, and do a direct computation basically. The scalar multiplication 1 over AD minus BC stays there, and then first row times first column, and then first row times second column, and so on and so forth. Do all those computation, and it'll turn out that after simplification, we're going to get identity matrix 1, 0, 0, 1. This is easier way, but it is possible to do this using Cramer's formula, and kind of strange way, but here we go. AD minus BC is the denominator because the Cramer's formula says, well, here we need determinant down here. And what's left over here is -1 to the I plus j power. So if I have 1, 1, then -1 to the 1 plus 1 power, that's positive. If you have 1, 2, then -1 to the third power, so that's negative. If you have 2, 2, -1 to the fourth power, that's positive, and so on. So we have plus, minus, minus, plus, as we have all those signs here. So what did it do? We took care of this scalar multiplication, 1 over AD minus BC, which comes from this denominator, and signs, plus, minus, minus, plus, we got those. And then how about these numbers? Well, these are coming from 1 by 1 determinants, of deleted matrices. So delete first row and first column, what's left is D. And delete first row and second columns, and what's left is C. And delete second row and first column, so what's left is B. And finally delete second row and second column, what's left is A. So we have the A11, A12, A21, A22 like this. And put those according to this Kramer's formula here. And then in the end, take the transpose. So switch these two. And what's left is the inverse matrix formula. So it does follow from Kramer's rule. But of course, this method is much easier proof. There are some examples here, but it's not the course related to that kind of example, so let's stop here. So we completed determinants, at least just the amount that we're going to need for lesson 15, or the latter 1/3 of chapter 9 of our textbook. So we'll stop here.